Oh, it's not touch. I thought it's more hi-fi than that. Hello. Can you hear me? Somebody, one of the online participants, please tell me.
Yeah, I can hear you.
Oh, good. Thanks.
Can we start?
Yeah, sure.
Welcome everybody. So in this afternoon session, we are going to hear about stone spaces and Boolean algebras and propositional logic by Professor Mohua Banerjee. She's currently the head of the Department of Maths and Stats, IIT Kanpur, and her research interests include rough set theory, modal logic, and algebraic logics. Over to you.
Thanks, Amit. So this is going to be tough because 3 hours cramming kind of what we do in a whole semester. However, I'll try. So basically, you will probably get some snippets of things that we do in the whole semester. So in order to get to stone duality, the way, and they want me to do logic as well, propositional logic. So what I'll do is I'll begin with classical propositional logic, transit into Boolean algebras, the connection of propositional logic with Boolean algebras, and then pass on to the finally into the duality business. All right. So some of the proofs will be detailed. Mostly tomorrow's results proofs would be kind of detailed. Others I would leave as exercises. I haven't yet had the occasion to pen down the exercises, but I hope is Prashanjit or Bidhan, and none of them is here. Anyway, so I'll just write down hopefully today and pass on for the tutorial tomorrow. So most of the exercises would be dealing with the topic that I'll cover tomorrow, but there will be some today as well. So we begin with logic here. So where we want to go is classical. Tell me if you can see, maybe there's too much light. Can you see this? Yes, I think it can be. It's visible. So in order to get to that, let me kind of briefly motivate by talking about what are known as formal theories. So these, in kind of our daily routine in mathematics, we encounter all the time theorems, right? Theorems, and then we prove those theorems. In order to prove those theorems, we may be utilizing some other results, which typically are called sometimes lemmas. So now to prove those lemmas, we may be using some other results and so on, right? But then this cannot just go on infinitely. So one has to start somewhere. And so that starting point would be kind of what you would regard as unquestioned or primitive statements, right? For which you do not require proofs, right? So those are usually termed, this word I'm sure all of you are familiar with, as axioms. So in formal theories, I'm not going to define anything formally here at this point. So in formal theories, the idea is that you start with a collection of axioms, which, as I said, are unquestioned or primitive statements that are agreed upon. So unquestioned by whom, right? That's a good question to ask. So by a community or by a pool of people. And so some may differ on what you are calling unquestioned. And so then that will result in another theory, right? So in a formal theory, what you do is you begin with some collection of axioms which are, you have arrived at a consensus with your fellow, group, and you talk of a procedure of deduction. So you will use some rules of inference, and then you start deducing results of the theory. You have met a number of these theories in your daily mathematics. So for example, you talk of group theory, topology, geometry, ordered sets that you have just learned, and so on, right? Now, so what but what happens is, so okay, let me just also add at this point, talking about this unquestioned thing. So for example, this the instance that I gave of geometry, all of us learn in school, right? The geometry we learn in school is actually Euclidean geometry. That's due to Euclid, postulates having been proposed way back in 300 BC, right? So so there were these 5 very famous, of which the 5th was the most famous postulate. And so that would serve as a very, kind of a prime example of a theory where you change an axiom and you get another theory, right? So you began with Euclidean geometry. The 5th postulate, that's a story in itself. I'm not going into that. But the 5th postulate was questioned, and for a time, not for a small amount of time, a huge amount of time, people thought that the 5th postulate would be deducible from the rest and so on. So that's what I meant when I said that's a story in itself. So however, the point is that the 5th postulate was questioned at some point, and we got in hand what is termed as non-Euclidean geometry, as in hyperbolic or elliptic geometry. So if any of you is kind of intrigued by this part of the history, I think you should really look this up. So this is one example of what can happen if you tinker with part of your axiom set, and you can get of course there are a number of other issues that I'm kind of glossing upon, like consistency and independence and all that, but it's just to broadly give you an example of what goes on when you look at formal theories. So now what we are trying to say is, underlying most of these formal theories that we encounter in our daily mathematics kind of scenario are some very fundamental statements or mechanisms of deduction that we do all the time, but we gloss over. They don't kind of appear before us that way. Okay, like what? So one example will, I think, instantly kind of catch your attention, which is that if you say that a statement A holds and the statement A implies a statement B, then usually what would we conclude? The statement B. So if I use this kind of a notation, so this is looking like a rule of inference, right? So you have a statement A, you find by some means, we are not going into how or why the statement A holds. Our point of discussion is that I have found that somehow that A holds, that the statement A implies the statement B, and then I am ready to conclude the statement B. So this is the very famously the rule of what is called modus ponens, or in brief MP, right? So this we use all the time. Like if you go back to your any mathematics textbook and look at a proof of a theorem, you would always see, okay, I have got this result, let's say from some lemma. Now I see that if I assume that statement, I get here. So of course I'll conclude that, right? So what are you doing? You're using modus ponens in that proof, right? So this is just an example. You have other examples, like you would want to conclude or you would want to regard a statement like this as true, right? So either P holds or it doesn't. What's to question about, right? Okay, you will be surprised. People may question that, right, under some situation. However, so this is something else that we always, use again in our daily mathematics. So either P holds or it doesn't. There's another thing that we do very frequently, and that's a proof by contradiction. But what's happening out there, if you just look a little carefully, you want to prove the statement P, you assume, if possible, that P does not hold. So in other words, what are you assuming? Not P. You arrive at a contradiction. Then what do you conclude? That your assumption was not correct. That means you conclude that not of not P is the case. Finally, what do you conclude? P holds, right? So what's underlying that? That in some sense, this is equivalent to P, right? This we blindly follow as well in our classical mathematics, right? However, this may be questioned. So for example, I mean, and you will meet this in the school itself when they discuss intuitionistic logic. So for example, if you are, trying to claim that there exists a continuous function satisfying something and something. So in classical mathematics, very often what we would do is suppose there does not exist such a function. You arrive at a contradiction and nicely conclude that therefore it's such a. However, there would be a community which will question that. Have you provided such a function? You're just giving us a roundabout method of concluding that it exists, but where is that function, right? So that's the kind of area which is called constructive mathematics. And in intuitionistic logic, in fact, one direction of this is precisely what is questioned and will not be accepted, and therefore you get a different logic. So what we are going to have is be more kind of faithful to what we do all the time. Unfortunately, non-classical logic does not enjoy any exposition in our school or college or anywhere. So it's kind of pushed aside as a very special topic and so on, unless someone focuses on it. So I'm glad that in this school, for instance, intuitionistic logic is going to be talked about. But anyway, so coming back, so we are going to, as I said, focus on, that's the classical part of it. All right, and also that, given a statement, either P holds or not P holds, this is another thing that we are going to assume. I will give you everything formally, but this is again part of the motivation that I'm trying to build up. Right, so this would be an axiom for us in some form, or would be deducible from our axioms. So I just want to, I raised this here in that okay, so under what circumstances could this be questioned as well? So this is like you're assuming that your statements can either be true or false and nothing else, right? So that, however, may be questioned itself. This binariness of the truth value set, so to speak, may also be questioned under certain circumstances, and you get this whole vast literature on many valued logics, all right? You introduce a third truth value, finite truth values, a whole continuum of truth values, and those may make very good sense in certain situations. All right, so that's another story, as I said, but we will make our life simple and talk of remain in the classical realm and about propositional. So we will talk of simple declarative statements. Those would be regarded as our propositional variables. Again, I'll give everything formally. Those would be, yes.
Will intuitionistic logic will define a new deductive system?
See, well, the axioms would be different. So therefore, a new system. But the underlying procedure that defines any formal theory, as I was trying to kind of broadly say, that you have a collection of axioms, you have some rules of inference, and your deduction procedure is defined based on those. That remains the same. That broad procedure remains the same. Now your axiom set has changed. So the results that you will conclude from those axioms will certainly be different from what you would get from classical logic. Yes, in that sense, a different system. All right. So, yeah. And propositional. Why propositional? So here we'll be just simply talking of declarative statements and connect those declarative statements with simple connectives of and, or, not, implies, and so on, which we will term as Boolean. All right. So we will not look deeper into the scenario, like we will not be talking of functions, relations. We will not be quantifying the variables of any domain, which would lead us to a very, very rich picture, and that would be called first order logic, which I presume is also going to be dealt with in this school. There, I hope you will be told why it's called first order also. Anyway, so again, that's a different story. We will make our life simple and talk of those very fundamental underlying sets of axioms and rules of inference, which will kind of, they underlie most mathematical theories. All right. So let's begin this with the language. So if I want to talk of some, statements and reason with them, so I'd better pinpoint what the language, how I express my statements, right? So I need that formal language in place, right? So the formal language, like our natural language, will have an alphabet, like our ABCs, right? So the alphabet for PL, let me abbreviate this as PL, I could write CPL, but anyway. So it consists of the alphabet, which has propositional variables, which were the simple declarative statements, as I said earlier. So which would be denoted as, let's say, PQR kind of things, or P1, P2, and so on. And this must already be giving you the hint that we will be talking of a countable set. So which could be countably infinite or a finite. All right. But let me just make this remark and pass on that that's not necessary at all. You can also start with an uncountable collection of propositional variables, fine. Any case, so as I said, we will be making our life simple. So let's not go into that. And then you will have what are called the logical connectives. So the connectives that are going to connect these propositional variables and result in compound formulae, compound statements. So what are those? So I'll introduce the notations that I'll be following. So this to stand for not, this to the wedge stand for and, the V to stand for or, and this is implies. Right? And you would also have parenthesis, the brackets that will give rise to formulae. Now the collection of formulae are what we will call well-formed formulae, WFFs in brief. So for that, we need to understand that given any alphabet, you can give rise to the collection of strings over the alphabet. So what are strings? They are just finite sequences of symbols coming from the alphabet. All right. So for example, here, even this is a string, right? However, these are not the kinds of things we want to deal with, right? They don't make any sense for us. So we will need to define what are well-formed ones that we finally would like to, handle. So this would be what is called a recursive definition. So you can put it in different ways. So it would be the smallest set of strings over that alphabet, all right, which contains the collection of propositional variables. So have I, no, I haven't abbreviated this. So let's call this set PV. So every propositional variable is going to be a well-formed formula for me. Fine. It will in fact be called an atomic formula because that's going to form the base of all my other formulae. All right. So these are termed atomic. And as I said, it's recursive. So recursive you can loosely understand as inductive. So what we have is then if you're telling me that alpha and beta are well-formed formulae, then using the logical connectives, I will build the set. So if alpha, beta are WFFs, so note that this is a unary connective. It applies on one formula, while the rest are all binary. Right? And so if I've said it's the smallest set of strings which contains this, then that's it. Nothing else can be a well-formed formula. Clear? So this is my set that we will. So example, P, is this a well-formed formula? It isn't, right? This is, of course, and so on, right? This is, and we have to be careful about the brackets. So for example, if I write this, then you see clearly that there can be different possibilities for this, right? So you can have left, associative and all that, but just let's be careful about the brackets. Fine, good. So now that well-formed formulae are clear to us, so propositional variables, as I already said, are supposed to be those simple declarative statements which take the value of true or false and nothing else. All right. So that's how we have. So now let's move on. Sorry. Because you can think of it as an inductive way. So you have the basis case where you have just the propositional variables, 0 connectives, and then you add the connectives and build. So inductive step will be all right. So any other questions, please, as I said, feel free to stop me anywhere. So that's it. So now I'll pass on to the axioms and rule of inference, etc. a little while later. But what else do we do with these guys, right? So let's move on to that one. So in other words, what is the semantics? We've already alluded to it now that a statement will be either true or false. So this thing is what's called semantics. That is, you are passing on from the syntax. Syntax means, strictly speaking, the language, right? So the symbols, the well-formed formulae, that's just a syntax without any meaning. So when you ascribe meaning to it, that's when you are passing on to the semantics. All right. So let's go move to that. And so we enter the picture valuations. So what are valuations? These are the ones that will assign meaning to any formula. So again, how we do that, because the definition of well-formed formula is itself recursive, how we'll define valuation will also have to respect that, right? So what we do is we begin with the definition of a valuation being, it's a map which goes from a collection of propositional variables, and we have only 2 truth values to refer to. And so you meet the set that probably has already been discussed in your Boolean algebra class, the 2-element set, right? So you've already met it. So you've probably met it in this manner. So 2 forms of Boolean algebra with max, min, and all that. You've already seen that. So here, just to keep the connotation clear, I may, interchangeably, so please excuse me for that. So I may refer to this as T, F with the obvious connotations, right? All right. So a valuation will then, given any propositional variable P, grass is green, sky is blue, it will assign it some value, true or false. Fine. So given that, now we would naturally not want to stick only to propositional variables. We will want to move to the whole set of well-formed formulae. So let me introduce another notation. So set of propositional variables is denoted by PV, that the set of, so these are my 2 notations for the moment, set of all WFFs, let's denote it as script F. All right. So we will extend this to abusing notation to a map from the set of all formulae to the same 2-valued set, but you can, I think, see what we will do. It will kind of behave homomorphically. So what you will do is, so this is a V which is being defined once this is given, right? So that V is given that I'm going to extend it to the set of all formulae. So clearly, since this is defined recursively, we will look at, say, a formula like this. So where will it be mapped to? It will be mapped to the 2-value set. And so in the 2-value set, we already have these operations, right? Which make it a Boolean algebra. So clearly we will take recourse to those. So when I take V of not alpha, and I'm defining it as not, please understand I'm abusing notation. This is in the syntax in our language, while this is in the set 2, the operation in the set 2. So obviously we would want to define it this way, right? And similarly for the others. right? And fine. So given this, we then come to just one comment on the truth table before I move on to a further discussion on this one. So these are referred to as these operations. The way they are defined, the tables that define the operations are referred to as truth tables. So just a couple of comments on that before I move. These are some things that we need to keep in mind because very often, some kind of confusion happens, which, for example, the way we define and is taking the minimum, right? If you look at the table for it, you will see that this operation is commutative. All right. So very often we may want to model a real life sentence with the help of, blindly with the help of this. But if you just think a little, real life sentences where we use and may not really be reflective of this one. For example, this is a patent example I give because it's very clear. Very often in natural language, the word and has a temporal connotation attached to it. So for example, we say that I fall ill and I go to the doctor. You don't want the other side to be true, right? I go to the doctor and I fall ill. So there's no commutativity there, in such cases. We, in mathematics, at least, we don't really want to bother about those things. So this is what I want to stress is the truth tables that we have here are really reflective of what we do in our daily mathematics, not always of what happens in how they're used in natural language. Similarly, when we look at OR, which is the max operator on 0, 1, it's not exclusive OR. All right, it's inclusive OR that the truth table gives us. Finally, the implication truth table, as all of you know by now, this is the only place where you have false. So think of it as 0, 1. Again, as I said, I'll just do it interchangeably, but this kind of carries the import better. So everywhere else, you have true, right? So it's only when your premise is true, but your conclusion is false that you would like to say, no, the implication is false, right? That's precisely the case when it's false, which means that when you have your premise to be false, you want the statement to be true. And that is not, you don't have to go very far to see the, like you say, the moon is made of green cheese implies something. But that entire thing implies 2 + 2 = 5. You would want, by virtue of this truth table, to regard that implication as true, however absurd it may sound. All right. But if, as I said, that's kind of dicey if you connect these things all the time with natural language statements. However, if you come back to our mathematics, that scenario is precisely what we term very often, term as vacuous arguments, right? So a quick example. So you say that A is a subset of B, because this may come back a little later as well. So you say a set A is a subset of B where both A, B are, let's say, coming from X. When do you say that? That for all X belonging to X, if X belongs to A, then X belongs to B, right? This is how you define inclusion of. Now, given this definition, one of the basic things that we always learn is that the null set is included in any set, right? That is an example of precisely that row of the truth table. Why? Just plug this in here, right? This becomes false. Then you regard this whole thing as true. And therefore, this is your conclusion. All right. So this is clearly that happens all the time in this one. And so I repeat, these truth tables that we are taking here are basically reflective of the mathematical arguments that we do all the time. Fine. Okay. So those were a couple of comments I had about the truth tables. And now we are ready that we have valuations defined on all formulae and those truth tables, to talk of the truth table of a formula. So for example, if I take, let's say, the formula P and not Q, what would we do? We would just, draw this table. What we would do here is list out all the possible truth values that these two propositional variables take, right? So that's clearly the way to define a truth table, right? So on the left of this, the first few columns, according to the number of propositional variables that your formula has, would list down all the possible truth values that those variables can take. So in this case, how many can there be? 4, right? So 2 into 2. So you have this. What are you doing here? You are just basically looking at every row, the valuation it defines, and applying that valuation on this formula and writing down the entry out here, right? So like if I were given V1, V2, V3, and V4, so V1 assigns both P and Q the value true. So given that, using this definition, what does V1 assign P1 and not Q? That's the question, right? So you will just plug the values in. So essentially, a truth table is nothing but giving us the distinct possible valuations that we can have. So if you have n propositional variables, the truth table of a formula containing n propositional variables, how many distinct rows in the truth table would you have? 2 to the power n, right? So each of this. Note one more thing, and that will bring us to the first result in this class, that note one thing, that I have really, so suppose my propositional variable set consists of P, Q, as well as, let's say, one more propositional variable, R. However, I am looking at the truth table of this guy. So I am just focusing on these 4 rows. So in other words, I am not caring about a valuation, let's say, call it V1 prime, which goes from this to 2, but which matches V1 on P and Q. But for example, is different for this. I don't care, as long as I am evaluating that formula which has just the variables P and Q. So that actually is a result. What is that result? So suppose alpha has the propositional variables P1, P2, Pn, and the valuations V and V dashed are such that V of Pi is the same as V dashed of Pi for all these. Then what are we concluding? In terms of the valuations, right? So if you have 2 valuations which match on all the propositional variables in a formula, then they match on the formula itself. This proof I will leave as an exercise. The proof will be simply by induction on the structure of alpha, so to speak. That is the number of connectives it has. So the base case will be when it's a propositional variable, 0 connectives, right? And then you do the other cases, right? So this is one of the simplest results that one begins propositional logic with. Let me at this point give you another proposition, which is also a nice result, that suppose my propositional variable set has these n members, and let me define a formula alpha as the conjunct of, I'll just in a moment I'll explain the notation, where the epsilon i's are either 0 or 1, and this entity is defined as pi itself when epsilon I is 1, and otherwise it is negation pi. All right. So in other words, what does that alpha look like? That alpha looks like something like P and the formula. If your PV is, let's say, P comma Q, then this, for example, you could think of as 1P and 0Q. Right? All right. Fine. So that's just an abbreviation that will come in handy a little later. That's why we introduced that one. So what about this kind of a formula? So such a formula will enjoy, or there will be a unique valuation satisfying. So when I use the word satisfying, I mean makes it true. All right. So there is exactly one such valuation. So those formulae are very, very special. Yeah, please.
Can I have a infinitely many is logical directives?
No. So I said that well-formed formulae are strings, and by definition, a string is a finite sequence. You cannot talk of that. All right. So that's completely restricted. So this is the case. And if you just give it a thought, I would leave this as an exercise. If you give it a thought, this is not difficult also at all, because how will you define that valuation? Let's call it V naught, suppose. What would you do? How do you define a valuation? On the entire set of propositional variables and then extend it, right? So the set of propositional variables are those P1, P2, Pn. So I have to give the image of V naught for each of these Pi's, right? So V naught of Pi, I need to define. Now Pi doesn't come just as it is. It is tagged with an epsilon, right? Which is either 0 or 1. Just look at it and give the truth value. If it's 1, make it true. If it's 0, make it false, right? And it's not difficult to see at all. So if you go back to our example, so if I had P1 and not P2, what is this V naught doing? It is basically making every component true. And that's precisely the condition of a conjunct to be true. Min operation is true when, or gets the value 1 when all the components are 1, right? So that's precisely what that valuation is doing. And if you change the valuation, what does changing the valuation mean? It has to differ on at least one propositional variable. The moment you make it differ, that component will become false, right? The entire thing will then become false, right? So that's precisely what's happening for these kinds of formulae. So these formulae are very, very special, as I said. Fine. So now we move to, yes. Yeah, tell me.
What was the meaning of a valuation satisfying a well-formed formula?
True. So I'm sorry, I use all these languages. So unique valuation, if you want to rephrase it, that makes alpha true. That so okay. So which means, so again, that true, you can think what is true. So let's call this V naught. Then you can make it further clear such that V naught of alpha is T. Right? Okay. So now let's move to some very special formulae, which, so I will try to hurry now. So, but anyway, given this whole scenario, I hope that so far things are clear, because this absolutely, fundamental things about introducing the language and valuations, there should be absolutely no ambiguity about. So we now encounter some special formulae, of which 1, for example, we have already met. So we already discussed this, right? So now in terms of these valuations, what is so special about this guy? And so what does it mean to be always true? So let's be precise now that we have introduced this formalism. So to put it precisely, what we are saying is that for every valuation, B of this one is going to be always true. So that gives us the first kind of special formulae that we call tautologies. So which are precisely of this kind. That is, a tautology is a formula which is true under every valuation. Every valuation makes a tautology true. All right. So there can be several other examples. So for example, if I just tweak that a little, this is also going to be a tautology, right? And so on. The other kind. Example. Or now that we know what a tautology is, so again, let me just write it a little loosely. So for example, I write it this way, but this I will be using a little later, so might as well fix it right away. That is, you choose and fix. There can be different approaches for doing this, but let's just do it this way. Now choose and fix any tautology. Okay, and denote it. So again, abuse of notation, but by top. All right. So if I were using LaTeX, it would be different. In any case, so all right. So if you have done that, then what I meant here was this. So you just negate any tautology. Yeah. No. So why are we confusing these two? That's for that very special formula, right? I did not say that that's a tautology.
Oh, I see.
Yeah. That's very different. All right. That's very special. Okay. That has exactly one valuation which makes it true. Right. And it's going to be false under every other. So there's no question of it to be a tautology. Right. Okay. So negation of any tautology is a contradiction, and similarly negation of a contradiction would be a tautology, and so on. Okay. The next kind, and that brings us to this fundamental notion of today's class, which is the notion of logical equivalence. So this is a relation on binary relation on the set of formulae. All right. So this is denoted by this triple bar. And so when do I say that two formulae are logically equivalent to each other? When there are a few ways of describing it, but all of course equivalent in the meta level. That, for example, you say alpha by implication. No, I did not introduce by implication. Sorry. So what's by implication? In the initial language, I had just this and, or, and not, right? So this will be abbreviated. I hope the online people are able to see it. No, they won't be able to see it. I'm sorry. So I don't mind erasing all this. So is the camera kind of panning the board? I'm just teaching. Oh, you are doing. Okay, fine. Okay, thanks. I mean, I tend to forget that. All right. So you had those primitive symbols defining the alphabet, given in the alphabet, right? So you had these. Now you can very well define some connectives. So this is the one that we'll be interested in. So this is a new connective we are defining in terms of the existing guys. So this is just what we think of as by implication. How do we think of a by implication? Alpha implies beta and beta implies alpha. So that's precisely what we will write down in our formal language. So it will be written as, all right. So coming back here, equivalently for all valuations V of alpha must be the same as V of beta, right? So they are satisfied or not satisfied together. Fine. There can be a third way of putting this one, which is that one may be inclined to do this, which is that if their truth tables match, but there's a catch there. You can talk of truth tables of two formulae matching, provided the tables are same. What does that mean? That the rows, the number of columns are the same. What does that mean? That they have the same number of propositional variables. But we are not restricting ourselves to that. For example, I would want these two to be logically equivalent. Does this seem familiar? You have met it in Boolean algebra. It's just absorption. So I cannot say the truth tables of these two guys are the same, because this guy has two propositional variables, that one has one. However, obviously, if you have two formulae which have the same propositional variables, then of course they would be logically equivalent provided their truth tables match. That's precisely what the second item is saying. Fine. So once you have opened this up, now you see you have this whole collection of equivalences coming up. For example, this. For example, do these look familiar? Similarly, you can have, sorry, yes, thanks. And so on. So these we would like to term as, associativity. That we would also like to term this as commutativity. The only catch is that we have this triple bar sitting here instead of the equality, right? So there's still a kind of a hurdle, but we can. So what's the immediate next step? You observe that this triple bar is an equivalence relation on the set of formulae. So you have reflexivity, alpha is logically equivalent to itself. You have you have symmetry, and you have transitivity, right? So you get the quotient set. So the set of formulae is partitioned. I hope that is, everybody here knows that, I hope so. Anyway, so an equivalence relation on a set can be translated or can be thought of as partitioning or giving rise to a partition on that set, right? So where every block in that partition basically consists of all the equivalent formulae, right? So for example, that P and Q, P or Q would be inhabiting the same class and so on, right? Okay, so coming to that one, and okay, so I'll just resist going into this next step immediately. But so now let's spend a little time on this quotient set. So what is this quotient set? So what did we conclude? Triple bar is an equivalence relation on the set of all formulae. We get this quotient set. So what's that? That is the collection of all equivalence classes, where what's this? This is defined as all those formulae which are logically equivalent to this one, right? Fine. Let's briefly look at the cardinality of this guy. So we began with the countable number of propositional variables, right? So the quotient set, so the alphabet, in fact, is also countable, right? The entire alphabet. So the quotient set in the worst possible scenario, where you have every class inhabited by a single fellow, would still have to be countable. All right. In fact, that's a general result. If you start with any countable alphabet, the set of all strings over it would necessarily be countable. All right. So now suppose I look at the other scenario. This was like in general that you have infiniteness also in the picture. But suppose I restrict myself to a finite set of PV. Then what happens to my quotient set? So that bit is also an interesting part of the story, which I also want to tell, which is that, so that brings me to this notion of a truth function, which is a truth function is just a function given a natural number n. A truth function for that natural number n is nothing but a function of this kind. So for example, you've already met all these guys. N equal to 1, negation is a truth function. N equal to 2, and or implies, all these guys are truth functions, right? So this is just a general term for that one. So you can have various others, right? So and or implies are, for example, very special binary truth functions, all right? But there can be others. So the importance of this one is that given, and that will bring me to another exercise, given any formula alpha, there is a truth function associated to it. So let's call it F alpha. What's that? It's nothing but the truth table of the formula. See, truth table of the formula I wrote as, PQR and the columns were like that, but just throw out the PQR and write that as, T1, T2, T3, for example. And because the entries are finally 0, 1 or TF, right? So effectively the truth table of any formula is also a truth function. So given any formula, I am able to define a truth function, right? And the interesting part is the converse is also true. So given any truth function, let's say f from there is a formula. Oh, I see. How does one? Yes, please tell me. Oh, I see.
Truth function is basically valuation.
Not really, because valuation, remember, valuation function gives meaning to a formula, right? So who is asking? Can I? Yeah, Bhargav, yes. So can you hear me? So truth function valuation actually gives meaning to a formula, right? So there is a level difference here. That means, so we went from set of formulae to T comma F, whereas here you are, so in some sense, that's what we are trying to reconcile with. All right. So we will say now that instead of a formula, you talk of, a collection of truth values, a sequence of truth values, right? And you assign, a truth value to any such input, right? So that's precisely where we are coming to. So it's not a single valuation. Please understand, truth table of a formula was not a single valuation. If you want to think in terms of truth table, right? So truth table actually consisted of all those 2 to the n valuations, right? If there were n propositional variables involved, correct? So it's more than that. It's definitely more than that. So come to this, I think this result will make things clearer. This association between, or this correspondence between formulae and truth functions. So this is one. And here, as I said, the converse. So if you go, if you're given a truth function, you have a formula. Okay, so let's denote it as AF. So AF such that F of AF, don't get confused with the notations. So what is F of AF? This I've already introduced out here, right? Given any formula, corresponding truth function I'm denoting as f of that guy. So now I'm saying that you started with an arbitrary truth function, and then you want a formula to come up whose truth table essentially is given by that truth function. This is what we are trying to say, right? And that is where precisely this epsilon IPI, that conjunct, will re-enter the picture. So why? Because of course that's subject to proof, but you need to do it. So suppose I'm given, for example, I have P1, P2, and again, sorry, you're given a truth function, right? So you have P1, P2, and the last column is T, let us say. So you have all these 4 rows, right? And you have some values here, I don't know what, so it could be TF, ST or something. So I don't know if it defines any familiar guy. I don't care about that for the moment. But the way we will get that AF, so this is my F, would be that I look at the number of number of variables that we have. So here it is 2. So to build this AF, I bring in 2 propositional variables, because remember the goal. I want the truth table of this guy to be just this, right? So I would replace this by P1, P2, and here I would have AF, right? That's my goal. So I want such an AF to come in, right? So how do we do it? Very simple algorithm. For each of the rows, I build the conjunct epsilon I pi for each row. What does that mean? So how will the epsilon I come? It will just be dictated by the entry there. So epsilon 1 P1 would be 1 P1. This would be 1 P2. This is 1 P1. This is 0 P2, and so on, right? So for each of the guys, you do that. Select the true rows and do a final disjunct of the conjuncts corresponding to only the true rows. You got the construction of AF. So AF is constructed by selecting these conjuncts that you built corresponding to only the true rows in this last column, connecting those conjuncts by a disjunct. All right. So for example, here I will just take this as, so this is P1 and P2. This is not P1 and not P2. So final AF for this particular table would be P1 and P2, or not P1 and not P2. Yeah. Has to be proved. Why should this work? Right? So what do we have to prove? That the way this so constructed formula must have just this as its truth table. Right? So that means given any valuation of choose any of the rows, then what that AF gets must be exactly the value in that corresponding in the last column. All right. So this needs to be proved. Fine. So what f of AF will, what we are claiming that f of AF will be just this, the truth table here. So you will just replace this by P1, P2, and this is your AF. Right. So that's the truth table. All right. So, but anyway, leaving that aside, what have we come to? We have basically come to a bijection between the equivalence classes in my quotient set and the collection of all truth functions. That is, if I take, so on this side you have this one, and so I have fixed the PV to be P1, P2, Pn, right? So again, I think they will not be able to see this, so let me do it a little lower. So this one where there are n variables, I'm assuming, all right? And here you have given that n, you have the set of all truth functions. Fine. Tell me, if n is fixed, how many such truth functions would you have? So remember, a truth function is t comma f to the n to t comma f. So how many? Yeah, 2 to the power. Right. And what have we got through these two results? That give me any equivalence class. I map it to, there's a catch out here, remember, which is always what we have to verify when we are dealing with equivalence classes, that this is just one representative you took. So you need to verify that this is independent of the choice of representatives, right? So if you take any other logically equivalent formula, a formula logically equivalent to alpha, you must, well, the truth tables should match, right? Or they should be. So here there's one small thing that's going on, which again I may leave as an exercise, is that even if you have a formula, suppose your total number of propositional variables is n, and suppose you're dealing with a formula alpha which has less than n propositional variables. So suppose you had 5 and your alpha you're taking has 3 propositional variables. You can always find a formula involving 5 propositional variables which will be logically equivalent to this guy. You can always find, all right? So given that one, so you can try that out for yourself. So given that one, this is going to be well defined, all right? And it's going to be a bijection. Thereby helping us conclude that in this scenario, this is nothing but this number. All right. So, well, there will be all these things involved. So for example, well defined is one thing. Then you want to show that for every, yes. So what is it? Yeah.
For given alpha, it is a small one, you can always class.
No, once again.
Given alpha whose string is small, you can always add something so that
Alpha is not varying, right? I didn't
no,
get
alpha
the
is
point.
equal to P1, P2, say P1
and P2, suppose.
and P2, say.
Okay.
Then you can add P3, P4, P5, right? Say, let's
But
say.
it's got to be logically equivalent.
Logically equivalent, so that
Okay,
it is okay.
fine,
But
fine.
this can be added in many ways, right?
Yes, sure. But
But
they will
see-
all be inhabiting one equivalence class, right? So
Yeah.
that's the point. That's why you've moved from the whole set of formulae to the quotient set. So you basically
This F alpha
identify
is independent of the
this what is?
F alpha is independent of the choice of
Yes, yes. That's
yeah,
the first thing I said. For it to be well defined, you've got to show that, right? So, so that was the other point that I just mentioned. That so that's going. It's going to be well defined. That of course that's the first thing one has to show, and then you move on to show that there will be a bijection. I mean, it will be a bijection. All right, thereby giving us that cardinality in the finite case.
Hi, I have a doubt. Hello. Yeah, so is F alpha?
Yeah.
Is F alpha some sort of simplification of every function corresponding to alpha?
What do you mean by every function corresponding?
As in every truth function corresponding to alpha.
So given a formula alpha, there is a unique truth function corresponding to it. This is what we mean. Okay.
Yeah. So I meant
define a truth function. Yeah.
So in tautology, we can have multiple formulae to get true all the time. So corresponding to that, the truth function will be just capital T.
Yeah. So all the
that is some
last
sort
column
of
will evaluate to true. True. Huh?
So do we say that that is the minimal number of PIs which are required to construct that particular truth function?
No. So we actually that's not relevant here. So what we just want for this result to go through is that you have given me a formula as that many propositional variables, and so for that we want a corresponding truth function that will simply be its truth table. All right. Now, if you happen to have a logically equivalent formula which can less number of propositional variables, you can always artificially put it up to give correspond to just that same.
No, my doubt is that there cannot be any equivalent formula which will have less number of PIs.
No, but why not? That's the example we just gave earlier, right? So you had P and you had so P1, and that's equivalent to P1 and P1 or P2, right?
No, in that case, P1 will be the truth function of this table, right?
Well, so what we are trying to say is that given any formula, we will always be able to see. So if you think of it in terms of this picture. Yeah. So, okay, I think I get your doubt. So let me try to answer that one. So suppose I have here alpha here, which and your PV was suppose cardinality is n, suppose, right? And so suppose this alpha has less than n, right? So suppose it has less than n. So in order for that one to be built, that correspondence to be built, I'm using this underlying claim that given any such alpha which may have less number of propositional variables, I will always be able to find in that same class another alpha prime which involves exactly this one, and then this entire class I will map to F alpha prime. This is what we are saying. Does that make it clearer?
No, I understand all this. My doubt is, suppose I get a truth function which has number of PIs, let's say small m, which is less than small n.
Okay.
Then I cannot find a truth function, or I cannot find any logically equivalent formula which has number of PIs less than small m. Small m was number of PIs involved for getting truth function.
No, but why should I'm not sure that's also correct. So are you saying that with the same number, I'm not sure I'm quite following what you're saying. Like what example can I give?
What is that we're not able to complete it, but we can always complete it to n variables.
Okay, I think let's get back to this, Bhargav. I need to just.
Yeah, sure.
Yeah, okay. So, yeah, I'll just maybe at the end of the class, I'll just get back to you again. Okay, sure. Okay, so. Right. So where were we? So in this in this quotient set, some special things start happening. So what is this class of that contains tautologies? So the claim is that there is exactly one class which contains all the tautologies and only tautologies. Yeah. Okay. So that means the two things that we are saying is that therefore that all tautologies are logically equivalent to each other, and if alpha is a tautology, right, or alpha is logically equivalent to a tautology, then so what are we saying here? Yeah, so if alpha is a tautology, like this usage of this T can kind of disturb. Alpha is a tautology and alpha is logically equivalent to beta, then beta is a tautology. Right. So the first one will ensure that all the tautologies are together in one class. The second one says that no other guy can come in. Fine. So you can understand similarly, you will have exactly a unique class where all the contradictions inhabit, right? So that's one thing. And let me see what else I have here. Yeah, so now let me get in the how much, about half an hour. Right? So, yeah, so that's fine. Yeah, okay, fine. So now let me come to in the last part of this one to what a study of logic. I mean, in various approaches, a logic is defined actually as a study of a consequence relation. So, so I'll slowly come to the way I kind of wrap up what I began with, deducing and concluding getting consequences from some axioms and so on. But before I go to that one, let us define what a semantic consequence is. So which is that all the time, so we have met tautologies, right, which are true under all valuations, right? But sometimes, so that means you, for a tautology, you don't really care about any assumptions. They are anyway going to be true, right? However, some formulae may be true depending on what you are assuming. Simple example is, suppose I take, we've already met this. Suppose you have given me these two assumptions, then from here, I would like to conclude this one, the MP, what we had already said. So in other words, what does this say? That if alpha and alpha implies beta are true under evaluation, then beta must also be true, right? So we generalize that one and define this one. So think of this as a collection of assumptions based on which you get alpha, to mean that if for any valuation V satisfies or makes all the members of gamma true. So I'm using the word satisfies. I've already explained that one. V satisfies all members of gamma, then V of alpha must be true. This is all the time we say this, right? If all my assumptions are true, my conclusion should be true, right? Then we will say it's a valid consequence, right? So, and please note this happens for any V. This thing, if you just denote as V double turnstile gamma, okay? So, sometimes this V is termed as a model of gamma, okay? Or it satisfies gamma and so on. So basically what it is saying is that any valuation that happens to be a model of gamma must be a model of alpha. So by model, I mean making it true, right? Okay, so notice that if gamma is empty, then what happens? So we have, so in other words, what we are asking is, what does it mean to have this, right? So for that, what we are saying, so by definition, what does this mean? So I will leave this as an exercise. It means that given any V, V satisfies the empty set, then V of alpha must be true, right? But look at, when does V satisfy the empty set? Careful, careful, very careful. So I've written this very clearly here. So V satisfies the empty set. What does V satisfy gamma mean? That if that given this V1, that V of gamma, so let's write it this way. So if gamma belongs to capital gamma, then V of gamma is true. This is actually the expansion of this one. Yes, so be careful. Don't say it's false. It's in fact vacuously true, because you're replacing this by the empty set. So this guy is always true. Where are we here? This is therefore true all the time. You want this entire thing to be true. It means this, it's forcing this one to be true under every valuations. So therefore,
essentially alpha is a tautology.
Exactly, exactly. So this is, so that's why, so you see how this vacuous things comes back, often. So therefore, it simply means that this one is nothing but, it is just, if I can write it like this, is that alpha is a tautology. Okay, so, and there's another way we put it, we say that alpha is valid and so on, okay. So now I will give some exercises on this one. Yeah. And, where, so that example I was giving, in this notation then will just mean this. So this is an example of gamma double turnstile alpha for you, all right. So let me end with this proof. So let me just go back to my axioms. And so I said that propositional logic we are going to pitch as an axiom, as a formal theory. So I have to say what are my axioms here, right? So what do we understand of axioms? As I said in the beginning, so axiom means some unquestioned true statement, right? So it should be valid under or true under all circumstances. This is our loose understanding, right? We now already know what that means. So those guys must be tautologies, right? So we can't just choose some random formula from somewhere and label that as an axiom. We need to pick out from the collection of tautologies. But which tautologies? There may be hundreds of tautologies, right? That's the challenge. So we need for a finite axiomatization, we are basically talking of some finite collection of tautologies coupled with the rule of inference that you can define a deduction procedure with. You will get hold of, you will be able to prove formally which are precisely the tautologies. So you don't get anything extra. So on the one hand, we had the tautologies. On the other, we are now talking of a deduction procedure where we make no reference to truth or falsity. We simply have a collection of axioms. We have a rule of inference. We introduce what is called a syntactic consequence. So that will be alpha can be proved from gamma, and in nowhere in this procedure do we refer to true, false, or anything. All right. So this is a different consequence relation altogether. But finally, what we should get, even if you ignore the gamma, so you call this a theorem, what you should land up with is precisely this or this, and conversely. So this should be our N. So whatever is provable should be valid or valid consequence and conversely. So then you will know what they say in literature, that your procedure or your system is sound and complete. All right. So basically, you have these two relations defined in two independent manners to be the same. All right. So what are the axioms for us? So I'll just state them for you. This is called the law of affirmation of consequence. Now just note. So as I said, it's a huge challenge to pick up from that basket of tautologies the ones that will suffice to lead you here. All right. It's absolutely non-trivial. One side will be trivial. That is, these guys are already tautologies. That's why I'm choosing them, right? Left to right, we expect to be easy, and it is. The converse is definitely non-trivial. Fine. So the second one is the self-distributive law of implication. So you will see why it's called that. So distributing over the implication. And the last one, so note so far negation is not in the picture. Third one brings that in, and that's the law of contraposition. What's the rule of inference? Our familiar modus ponens. How do I define the turnstile? Very simply done. We say, though this is, so this is the axiomatic method. So what we say is that there is, so this is just, kind of formalizing what we had in our mind, what we were visioning, that there is a finite sequence of formally, let's say alpha 1 to alpha n, such that alpha n is alpha, and for each I, alpha I is either an axiom or belongs to gamma, that is, it's an assumption, or is derived from the previous members of the sequence by using the rule of inference given. So in our case, MP. So it's basically something like this. I'll quickly give you an example, but this is by no means very easy or something. It's tricky. So it's not, it doesn't come naturally. So there are various proof theories various proof theories, I mean, various ways of defining the singleton style. This is one that I'm saying, giving you. But in all the cases for classical propositional logic, there are various ways of defining the singleton style. But at the end, net result is singleton style is equal to the doubleton style. Doubleton style is defined in the same manner. All right. So here I'll just quickly give you, for example, this we know is a tautology. I'll give you a proof for it. So how do we do? So there's no negation here. So we clearly do not expect this third axiom to come in. All right. So what you do is you just begin with, so this is your first step. Let's call it alpha 1. So this is my goal. So let's call it beta. Okay. So we want beta to be a theorem. So when gamma is empty, that means you just drop this clause. Then you're basically saying that you have a number of steps, each of which is either an axiom or, use MP on the previous, you get to the last one. So that's what this example will be about. So for example, you begin with this one. Then in the next one, you see, I can just do a self-distributive, that second axiom. So I skip some steps. So, okay, let me not skip. So this, I am skipping a step. Okay. So, so the intermediate step would be just this guy. Okay, gamma. If I call this gamma, then gamma implies this entire thing. Okay, let me write this down instead of creating confusion. Alpha 1. So the next one will be, just write down that axiom applied to this formula. I hope that's clear. Okay, I've just used A2, the second axiom. So this is my alpha 2. But then I am ready to use modus ponens on it. Because note, this portion and this portion is the same, right? So therefore, I get that. Right? So this is by MP. Right? So legitimate. So this is my alpha 3. So alpha 3 is obtained by using MP on the previous members, right? Now, this is alpha 4, but this is already an axiom. Please note here the axioms. In the axioms, the beta, gamma are variables. So they can be just any formulae, all right? That's why this is called an axiom scheme, all right? So I don't want to go into that, but just understand that those act as variables. So this one, so again MP. So you'll get the last step. So this is your alpha 5, which is nothing but your beta. MP on alpha 3 and alpha 4. Right? Okay. So just to give, but I think you may be understanding or feeling already that this cannot be so easy. But you kind of make your path easy by proving some nice results, and then you like what's called the deduction theorem and so on, which then help you to kind of deduce more, theorems and so on. So anyway, what I'll just come here to is, yes, I know that. Just give me a second. Yeah. So we are. These two relations are just the same. Exactly. Yeah. Yes. So yeah. So that in the last 5 or 6, 7 minutes or whatever Amit told me, let me just point out that the importance of that quotient set again. That so I will not be able to show that those two are equal and so on, but I'll just come back to that. For that, we have to note that this guy forms a Boolean algebra. We've already said that there is a unique class which contains all the tautologies, a unique class which contains all the contradictions, and I'm claiming that there will be other operations that we can introduce to make it a Boolean algebra. So how do we define this? Now, please note, these are all happening on equivalence classes. So we are trying to figure out what this will be. Natural candidate, which is, and so similarly for the others, right? Negation. So these are all induced by the language. So remember, when I listed all those logical equivalences, I said that they are very familiar: De Morgan, associative, commutative, all that, only that triple bar was sticking there. So actually now, once you induce these operations on the quotient set, with this definition, of course, there's another, again, you need to verify that these are well defined, right? So each of these you need to show are well defined. But note then that here you will get the equality. Simply because this is alpha and beta's class, this is beta and alpha's class, both are logically equivalent, as we've already concluded. Now the classes become equal. Okay, so this quotient set forms a Boolean algebra, which is famously called the Lindenbaum-Tarski algebra. Some people call it Linda and so on. So this one, and to prove this is equal to this, the other direction, which we said is non-trivial, this thing, you actually utilize this one, the Lindenbaum-Tarski algebra. All right. And also another thing, note that evaluation was defined as going from this one, right? So I'm just now slowly bringing back Boolean algebras into the picture so that I go into the next thing tomorrow. So 2 is a Boolean algebra. Why restrict the definition of evaluation to a Boolean algebra, to 2 in particular? Can we replace it by any arbitrary Boolean algebra? Why not? Because what was the next step? We extended the definition of valuation to the set of all formulae. How did we do the extension? For example, we took this to be this, right? What was this? This was an operation on 2. It exists in any Boolean algebra, right? So therefore, you can still do exactly the same thing for evaluation by just generalizing the picture, so to speak, from 2 to any Boolean algebra. All right, and then you have this one, which is just a generalization of, which is just saying that alpha is true in every Boolean algebra. What does it mean? That for any such valuation, so this notation means for any such valuation, V of alpha is the top element of that Boolean algebra concerned, right? Given this, I think you can immediately connect back to what we discussed as the double turnstile. So what we have already met, this one is nothing but this in this notation, right? Is that clear? Because this was what? For any V alpha is true. That is the top element of 2, right? So once you have generalized it to this level, now notice we still have one level still lurking with us above, which is why stick to one Boolean algebra? Let's vary that whole thing. So which means that you can talk about now this notation, meaning that so where B means this, the collection of all Boolean algebras. So you got the different steps. So we have generalized the definition of valuation, replacing 2 by any arbitrary Boolean algebra, then defined Boolean algebra, so to speak, that is evaluation on a Boolean algebra, make it go to the top element of that Boolean algebra. Now you vary the Boolean algebras through the whole collection. So given any Boolean algebra, is alpha true there under every valuation, and you get this one, right? So then the question is, we've already defined this because we are still talking of formulae, right, of our propositional logic. What about this and this? Right? But actually still this is the same. So that's the power of 2. And that's where I will end. Why is this the same? That's just a one-line argument. Because from here to here, that is, if I have alpha, that implies this one is very easy to check, because you will just take the axioms that I've defined and show that they're all true in every Boolean algebra, where you will define A implies B. I don't know if this has been done. You just define that as not A or B, because implication was not present in the initial definition of Boolean algebra. So you just define it this way, right? And then you just look at things like this. Okay, this, please note, will always be 1. Okay, because this is not A or not B or A, right? So not A or A will always be 1. Okay, so all the axioms happen to be true in every Boolean algebra. So this direction to this direction is anyway true. For the converse, suppose this is the case, means in every Boolean algebra this is going to be true. In particular, in 2 it's true. But so as assuming that, you know, our old double turnstile is the same as single turnstile, that means 2 double turnstile alpha should mean, this will mean this, but that will mean, right? So that's where I will end. So tomorrow the plan will be, so basically what's happened is this should be indicating the power of 2, and that's for good reason, because what we will be talking about is representation of these Boolean algebras, where this power of 2 will, you know, revisit us. Okay, and so the tomorrow's plan will be this. I will see how much I can do of the proofs. Maybe I'll skip the proof. So I will again reinvoke this quotient set. You have learned what atoms are, right? So this Lindenbaum-Tarski algebra being a Boolean algebra, let's look at what the atoms look like here. Okay, because we have spent so much time on understanding this one. So let's actually see concretely what they are and what kind of Boolean algebras are formed by this one in different cases. All right. Then once that's done, we will look at the representation theorems. That is, given an arbitrary Boolean algebra, I'll split it into 2 cases, finite and in general. What happens? So what do we mean by a representation theorem? And then we'll move over to looking at the, you know, the representative objects, how they look like. Okay, so that's where the topology thing will come in, and where what you have learned in your topology lecture will hopefully you know, come in handy. So we will look at it from the topological angle, and that's what we will mean by the duality. That is, transit from Boolean algebras to a kind of a topological space, and conversely. So that's will give us this tight connection between those two. That's what we will mean by the stone duality. All right. So thank you. I hope something went across. Thanks. Yeah. So I don't know
yeah. Do we have any quick questions? Only one or two. Online or offline?
Yeah, sure. So you can tell me if this was too fast or what, you know, any of here or there, you know, or was it very elementary? Should I speed up? I actually don't want to speed up, even if some people want me to. Yes. Because I'm not sure this is familiar to, you know, many. Yes, tell me.
Being single turnstile equal to double turnstile,
right.
That means that something that is provably true in syntactic.
Don't say provably true. These two are different things. What is provable is true under all circumstances, if I want to put it loosely. Conversely, what is true under all, now the circumstances we have formally termed as valuations.
Yes. So,
yeah,
so
and conversely.
So in valuations, if a well-formed formula is true, then there's a proof for it. And
correct. Not under one valuation. If under every possible valuation it's true, that means it's what we call a tautology or is valid, then there should be a proof for it.
Yeah, that is what is meant by single turnstile.
That there is a proof for it is what single turnstile, precisely.
All and right? The other side also.
Correct.
Which is simple.
Yeah, absolutely.
Yes, Anand.
Yeah.
You can
Am I
talk.
audible now?
Yeah.
Am I audible now?
Yeah. Please speak.
Yeah. So my question was about valuations and the Boolean algebra. What we did was we looked at the function from the set of propositional variables to the underlying set consisting of two elements, and we said that we can extend this to the entire set of well-formed formulas to the Boolean algebra of two variables. So I was wondering, is this some sort of a adjunction that's going on here? Is this, can we think of the set of well-formed formulas as a sort of a free algebra generated by this? Like, for example, like the set of, we have a function from the set of propositional variables to the set 2, which is like a set theoretic function. And on the other hand, we are extending this to a Boolean algebra homomorphism on the other side. So it seems like there's one underlying set functor over here, and there's a free functor on the other side. Is something of this sort happening over here?
If you can call just the set of formulae, it's not just any set.
Yeah.
So I don't know.
I don't think you can call just the set of well-formed formulas as anything. You have to get down to the level of equivalence classes.
When you're
Okay.
there, then
Once we have the equivalence classes on them, will this be like some sort of free and forgetful adjunction?
You have one Boolean algebra on one side and what on the other side?
So I'm sorry, I'm not able to hear you clearly.
Am I audible now?
Yeah.
Yeah. I'm saying on one side you have got Boolean algebras, and what on the other side?
On the other side, it's just sets. So like we have a set map from the set of propositional variables to the set of two elements. And then we are extending this map to a Boolean algebra homomorphism from the free algebra, from the set of all well-formed formulas to the Boolean algebra on two elements.
No, but the set of all well-formed formulas is not equipped with any kind of algebraic structure. That's the problem.
So again, like I think there's an audio
he's
issue.
just thinking of it as a set, I think.
Yeah, it's just as a set. No, I don't think that.
So again, I think there's again an audio issue.
It's making sense.
What?
I think that's again an audio issue. I'm having trouble hearing you.
Or maybe this microphone is dying. I don't know.
You can take this.
Hello. Am I audible?
Yeah.
Yeah, I'm saying that on the set of well-formed formulas, you don't have any algebraic operations, and therefore you shouldn't expect anything.
Okay, but we have the operations of conjunction and disjunction and so on. Like we can.
Yes, but they are not really like.
We don't get equality or anything,
Yeah,
right?
it's
Those are all syntactic entities simply. They, as such, they don't make any sense. I mean, you just have some syntactic, strings, as I call them, alpha and beta, alpha or beta, and so on. And once you come to the quotient set, you are actually just talking of a Boolean algebra again. So
Right,
the
but,
question of
like the
forgetful functor and all that, right?
But the valuation, like at least syntactically, it looks like a homomorphism, like a Boolean algebra.
It is. So on a Boolean, yeah. So I mean, I don't know whether to actually look at it as a homomorphism in the algebraic sense, but it is extending in that sense. Yeah. So if you look at the quotient set, then maybe you can think of it homomorphism from classes here. I don't know. Yeah, we'll just think about it a little. So now you have all the entities in front of you. So,
can I just add one sentence here?
Yes, please. Yeah, please.
Now, perhaps his question may be addressed in the following way. The underlying algebra, if we consider the base set, that means the formula set with the operations as an algebra, there is no harm in it. But problem is this, that it will not turn into a, you cannot make it a you cannot develop partial ordering there. Because you can perhaps say how can you say that alpha less equal to beta or something like this?
Or alpha equal to beta. That's precisely the point. Yeah. So
Yeah. So
this is why we went over to the quotient set, right?
Right. Another thing I realized is that like commutativity of all the operations like or and like they're not built in. Like
No,
they're
no.
True.
That was precisely the point I was trying to make, right? You
Yeah.
have the logical equivalence, but to talk of it as an algebra, you need inherently an equality, right?
Right,
To,
right.
you know,
Yeah.
to talk of equations, you don't have that, right?
Okay. Yeah.
No, the point is this, that equality, one can say that alpha is equal to alpha. That's all.
Yeah, but at least you need to
That is
look at it as an ordered set, as you're
Yeah.
saying, right? So even a
Right.
partial order, you're not able to build. Yeah.
Okay.
So partial order, it is not becoming partial order. On the other hand, as soon as you make it you just take this equivalence classes, it becomes nice algebra. It becomes partial order, and then it becomes lattice and so on.
Right.
Okay. Thank you. I think it makes sense.
Thank you. And Gaurav, if you can just email your this thing to say no, the other person who asked earlier, I didn't answer.
Bhargav.
Oh, sorry, Bhargav. I'm sorry. Yeah. So if you're still there, you can maybe mail the thing or.
Yeah, I'll mail it to.
Yeah. So then, because we don't have time, then I'll definitely want to answer that. Okay.
Yeah.
Okay. Thank you.
Okay, thank you. So we'll start after a quick 5-10 minutes break. Yeah. Hello.
Okay, so online participants, please turn on your videos. I want active participation. I feel that faces reveal a lot of things. Okay, so the link has been shared on Zoom and you can find it on ISLA website as well. Here. All right. So there are two sections in this tutorial. One consists of basic questions. Some of the basic questions still may be challenging for you, or at least somewhat difficult. There is another section which is hard, but that is not so hard as you will see. Okay. Try solving those exercises. The exercises are in a linear fashion according to the talks. So, right. And you'll find exercises about only things which has been covered. You can start. Yeah, just refer to me. कोई सवाल? Whenever they ask, you can start maybe. Okay. Yeah, I mean the mic. Still people did not show their faces. I don't know whether they're solving, but please ask if you have any doubt. Yeah. So अच्छा इसको हटाऊं क्या? Sorry, should say that.
We should look at the faces.
No, this was a grid view.
Yeah, that's okay.
Yeah.
Take some time to read the questions and then you can see that.
There are way too many.
Some of those questions are not difficult.
You just go through them, whichever you find easy, you solve them. As I said, it's not really a. So this division of basic and hard is not really concrete. Hard questions are there in the basic section maybe, but just try whichever you can do.
Most of them, you can solve them by one or two unravelings of definitions. That it's
You can speak maybe. If you want to discuss about a question. No, not. There are only 20 students. How about the first question now? How about the first question? You have just seen the definition of a natural transformation, and you have also seen how you can visualize groups as a single object category. Now I want to show you that in fact, this has been shown that group homomorphism is just a functor. Now, moreover, I want to ask you what should be a natural transformation between group homomorphisms visualized as functors. And the question states that it has to be one element in the codomain category or the codomain group, so that for every element M in G, Fm is a conjugate of Gm. How about this question? Did anyone attempt this question?
Yeah. So there can be only one component in the natural transformation, and the condition you get.
Just
Like keeping
who is this speaking?
Anand.
Okay, I cannot see you, but yeah, go ahead.
Right. So there can be only one component in the natural transformation, since H is a single object category, and so we get, like, keeping in mind that composition of morphisms is the same as group multiplication, we get XF M equal to GMX for all M
Right.
elements of G.
Right.
And then, like, since this is a group, every morphism is invertible, so we can bring it to the form
Yeah.
Fm equal to X inverse GMX.
So that is the solution. Did everyone hear that? That is a correct solution. So he says that since on the domain category you have a single object, so you are going to have a single component of this natural transformation, if at all it is there, right? So as natural transformations were defined from category C to D between two functor F and G, a natural transformation alpha had its component given by C, inside objects of C, right? Is this visible? Okay. Still. So since the domain category, G viewed as a category, has a single object, if alpha is a natural transformation from F to G, then you're going to have just alpha star. If you view G as a category with star as object and morphisms as element, then you are really going to have a single morphism in H, which is going to be from, let's say, F star to G star in this case. And this was the single object in H. So this is star H to star H. Now you want commutativity of certain diagrams. I use colored chalk. Okay, I guess this should be, yes. So that's the idea. You have a single component, and then there has to be a commutative square for every morphism in the domain category. You try that. That commutative square will reveal the relation given. Yeah. Anyway, I have verbally cleared it. So I hope the idea is clear. If anyone still having a doubt, then please ask. Is that clear to everybody? Anyway, you learned something.
Yeah, that's good.
Right. Is this clear to everyone? No.
Just
Offline participant?
define the conjugate.
Sorry?
Conjugate.
Yeah, so that is just a name, which means this relation holds.
Oh.
If anyone knows group theory, then they would be familiar with this term. But that's just a name for the equation given. Offline participants, this is clear. All right. Let us treat the second question now. Oh, I see. Where? Thank you. Okay. Right. Yeah. Someone cleared the solution before me. He gave the solution. I elaborated on it.
You can call someone from here to write something.
This equivalence. But yeah, you can solve any of them. Sorry. Yeah, that's a good idea. So let's turn our attention to question 2. Does everyone? Okay. I'll ask online participants first. Is the question clear to you? Even offline participants. Is the question clear to you? Question 2. Huh? Go ahead. No, right? Okay, let me try to explain this.
I
So,
didn't understand this inverse or antisymmetry, but
sorry?
the idea of inverse or antisymmetry.
Yeah, so you know what is an inverse to a morphism in a group, to an element in a group, and the idea of antisymmetry in a pre-order, right?
Yeah.
So
that's what is meant here. Okay.
Yeah. Is this clear to you? So the question? Yeah, sure. Go ahead.
Do we use the concepts of left and right inverses in this?
Inverse for what? Left and right inverse for?
For any morphism, let's say small, in a monoid.
So a monoid is some sort of a general structure than group. In a group, you have a associative binary relation, which is also there in monoid. But in monoid, you do not have the idea of an inverse to every element.
Yeah, that's why I said so. Left and right inverse.
Yeah. An element might have an inverse, might not have an inverse in a monoid. Think of how I defined isomorphism in a category. Did anyone solve this question? No. I'll give you some hint. How was an isomorphism defined in a category? A morphism is an isomorphism if there is another morphism G such that, yeah. So this was defined such that G compose F is identity on A and F compose G is identity on B. Now think of a monoid, which was a group without this notion of inverse to every element. Then what is a morphism? So there are only one object, right? You have a single object in a group. And what is a morphism there? It is just an element R in this group G, or a monoid. And then these would be an isomorphism in the sense of categories if there is a morphism in the other direction, let's say S, but that has to be an element in G. And what was the identity on this object? This was precisely the identity of the monoid, right? So that means you have to have that S compose R is E and R compose S is also E. So there is this E. This has to be there, which means that they are invertible in the sense of monoid or groups. If you go to partially ordered set, then think of this, what this should be.
Only identity will have inverses.
Yeah, so if you think for posets, then it is the case, right? But in a pre-order, more generally, if you impose this condition that there is an isomorphism, then think how it is going to be. In a poset, this is going to be the case, only the identity, because there you have this antisymmetry. But if you remove this antisymmetry condition, then it is telling you that X is less than equal to Y. So if X is less than equal to Y in a pre-order, there is a morphism. Then Y is less than equal to X. That is, there is a morphism from Y to X as well. Right?
So is question 2 clear to all? Is there someone who didn't, who is still at loss? We can explain. Okay.
No. So
okay, try more questions. You can try questions in any order, but
yeah.
Inform us if you feel at loss. And we will remain in order, and we will next ask question 3 if you are okay with it.
Question 3 was introduced in lectures. Question 3 was introduced in lectures.
Yes, question 3 was introduced in lecture on natural transformation today, yesterday. In fact, it was the motivating example. I just want you to fill in the details there. A first hint will be to first revisit your notes and see where the functor, the domain and codomain categories of these two functors are. And then you can move up from there.
if students are attentive, they should have already done this as a homework, but is there any online participant who is trying hard questions, though they are not hard as such? I'm just trying to confirm if there is any need to put hard questions in that case in the next tutorial.
So anyone with question number 3, would anyone would like to, is there anyone who would like to explain question number 3? Or would you like us to explain?
He did that already. He did that already in the lectures. Explained it so many
Okay,
times.
let me help you. No. Let me just at least draw the functors. That will be a start.
Nobody is responding to what you are saying, so I will want to do it anyway.
Is it audible? Just ask them. Are you audible or not?
Am I audible? Anyone on chat? Can you please confirm?
Yes.
you are.
Okay, thank you.
The particular minutes, ask them what they are doing.
Okay. Anand, are you there?
Yeah, I am.
Did you try question number 3?
I was actually looking at question number 6 right now.
Yeah, okay.
Like I was.
Have it your own.
Yeah, so I haven't read. Yeah, I haven't. I'm not going in.
Yeah, okay, no problem.
Ask for offline participants.
Anyone from offline? You were able to do it?
You already did it, no? So why you are not going to the board and give the answer?
Great.
So Nitish will explain.
Whatever we are, they will take the determinant of.
Talk to the audience. Right?
They will take the determinant of it
You might just talk.
Talk to the mic, yeah.
and determinant. Then we will again take determinant of it. It will change ultimately nothing plus. It will take ultimately nothing because it's like we are taking determinant of units and ring and ring.
You begin with determinants of a make.
Yeah, we started from here, and whatever it started, and it will give the same because it's a whatever the unit we will get.
That will be the determinant.
Yeah, and it will be for this corresponding.
Okay, so where are you beginning from? Like what's your starting? Can you draw the GLN functor? You can erase this and then start from the.
Like we are taking. I don't understand.
Draw the GLN function. As the diagram.
This is the representation.
That is for natural transformation. Why don't you write down what GLN is as a functor? It starts at a category and goes to a category, right?
It's an object in a category to another object in another category. Okay, 1 second.
Let me explain it as a functor first, and then, like, once you have settled on both the functors, then try to do the.
So natural transformations are defined for functors. So if you have to show that there is a natural transformation between two functors, so you need to first understand those two functors. Right? Yeah. So the first goal in this question is to look at what those functors are. Those functors are GN, this functor which takes any commutative.
Anything from the online participants? You can ask me any question if you are trying in any order.
Takes commutative unit of range
Can you explain question number 5? I don't know
Yeah.
what it's
Right.
going to show.
Did anyone try this? Did you try this? Did you try this? So given a PO set, you collect all of its town set. You want to make it a topology. Yeah. Is that understood first of all?
Yeah,
To
that's fine.
collect-
But,
Sorry,
yeah, that part is
clear.
yeah, clear.
But
I mean,
now you want to show that it's a functor. For that, what you need to do is you need to give assignments on morphism level, right?
Yeah.
Right. So on one hand, you have the category of PO sets where morphisms are order preserving maps, right? Order
Yes.
preserving functions. So you want to send it to the corresponding topology.
Hmm.
So
So it's a functor from POSIX to
PO set to topology.
Okay.
Now try. Okay. Yeah. So if that is an equivalence, right?
Talk about which question.
It's Q6.
But that's a direct message, so nobody knows what you are talking about.
Oh, I'm sorry. Yeah.
Yeah.
So Vargav, to your question about question 6. So when I'm giving you an equivalence F from C to D, I'm also giving you another data to this, which is
Yeah.
a functor from D to C.
Right.
Now, if you understand what I mean by F op, then you understand that this is an equivalence. Well, do you understand how F op is defined?
Yes, by yeah, I understand how FOP is defined.
Yeah, so you send object to object and f op small f op to f of that
Right.
op. Yeah, so right. If you understand that, then you define g op in a similar fashion.
Yeah, right. That's what. So that it's
Yeah.
straightforward, right? There's nothing.
Yeah. Yeah.
And be careful while using the word
Inverse.
inverse. Yeah, functors don't have inverses.
In equivalence,
What are
you
they
don't call
called?
it inverse. Unless it is an
What are they called?
isomorphism. So in isomorphism, you can call it inverse, but in equivalence, you do not call it an inverse.
So what is G
Because-
then of F?
What is G that we cannot control? There could be multiple G's,
Sorry. Yeah.
but the fact is that any two such G's will be naturally isomorphic to each other, which means there exists a natural isomorphism between them.
And much less effort is used to.
Okay, yeah, that makes sense. But then what should F G be called of F? Like we say G small g is inverse of small f in isomorphism case.
No, you say
There's
that
no word as
F, so the question should read that suppose F is a part of an equivalence.
okay.
Then there exists some G such that F comma G is an equivalence. And then F op comma G op will be again an equivalence.
There exists a continuous map between the images of the POSIX. Is this what
So
Yeah,
there exists
yeah.
a G such that
You have
F
to
of G is
construct a map
identity.
from this
E of F is
Sorry?
also identity.
first of all, yeah, that you have to do.
Loudly, Bhargav.
So we say that there exists a G functor G such that F of G is identity on the appropriate
Is
category.
isomorphic to identity functor.
Yes.
Don't say equal to. We are so much used to to use equality in mathematics, which shouldn't be.
Right.
As Deepankar mentioned today, equality is an evil concept.
Right. Yeah.
Okay, I'm going to go one by one. So Krishnendu, Which problem are you trying?
No, I'm not trying anything actually.
Then why are you sitting in the
Are you
tutorial?
trying- Yeah.
Oh, okay.
Yeah, for this to be a natural transformation.
What is commuting?
So, uh-oh.
This function is between elements of R.
So it's not this diagram commuting. There is no commutation here. If you want to show that alpha determinant is a natural transformation,
If
you mean that this is.
participants, please mute.
Oh, sorry. Just a minute. You can mute me there. No?
Any other online participants? Ritu, Indoria? Which question are you trying? Don't just attend sessions for marking attendance. Devanjan Chakravarti.
I'm trying the sixth one, where we have to show the equivalence of categories when considering the opposite function.
Yeah. Suyash Srivastav.
I'm still on third question.
Okay. So do you want any explanation on the third one?
No, I'm doing it on the second part of.
Second part, okay.
Showing that it is a.
Okay, I'm calling Animesh, she's explaining. Third question. Oh, he's trying.
I'm trying one by one. I think I'll.
Oh, you want to try it yourself? Fine. Aditya Gupta. Neha Gaur.
Hello.
Yeah, Neha.
Sir, I'm trying question number 7. I think I can do. I'm trying.
Question number 7.
Yes.
Okay, so can you tell me what is the terminal object in the category of sets?
It's the empty function.
Huh?
Like singleton set. Singleton set.
Singleton, very good. And what will be the terminal object in a poset thought of as a category?
Poset. Okay. So, in case of poset. Try.
So note that the definition of a terminal object says that if you have,
Yes,
you
it
should
is
have a
clear. It is
unique
clear.
morphism.
Yes, yes. Then,
In a partially ordered set thought of as a category, you have at most one morphism. Which
yes.
means in this case, you must have a morphism. So all your elements should be less equal that object. Now, can you tell me what it is?
Strictly ordered. Sorry,
Huh?
sorry. Less than. A function sending the maximal element. Sorry.
Exactly. The maximum element, not maximal. Okay, maximum.
Okay. Maximum.
The top element.
Yes.
Yeah, the top element is the terminal. Okay, so now keeping that in mind, try to approach the problem.
Okay.
Shriram. Anita.
Yes,
Which question are you trying?
I'm doing the sixth one.
Okay. Is it hard or easy?
It's it's a little hard.
It's hard, okay. So what is difficult in this question? Can you tell me? Did you understand the concept of opposite category?
Yes.
Okay, so in that case, can you define what is capital F op?
Capital F. Okay. It should be D goes to C.
No. So it's given that it should go from C op to D op. So object to object map, morphism to morphism map.
Okay.
What's an object of C op?
Wait, opposite map, it should be the reverse. Okay.
What is reversed in the opposite category?
The order of the morph, if it's going, the domain and range are like switched.
Right, but the objects will still remain the same.
Right, okay, yes.
Okay, now can you tell me where is F op taking objects of C op to?
To D op.
Yes, but which object? So suppose A is an object of C op, where will it be mapped?
In itself?
No, if you map it to itself, it will again land in C. You don't want to land in C. You want to land in D op. So therefore, if you start with an object F of A of C op, then you already know what to do with objects because F is given. F is from C to D. So you map it to FA.
Okay.
FA is an object of D, but objects of D op and objects of D are the same.
Okay.
Okay, so that is the object to object map. How is the morphism to morphism map defined?
That is switched.
Yeah, I mean, so capital F op of small f op, what is that? Maybe I will use the board and write something. This one. So F from C to D is given and F op is defined on C op, where an object A will still be mapped to FA. And whenever there is a morphism F op from A to B, where B is mapped to FB, then this F op will be mapped to FF op. So really speaking, what is happening that there is a morphism from B to A in the category C. This is happening in C op. This is happening in DOP. And what really is happening, that you had a morphism from, so given a morphism F, I have FF from FB to FA. That is given to me. But I'm simply reinterpreting that F as F op from A to B in C op and FF op from FA to FB. So what is your definition? That F op of small f op is defined to be FF op. Now this you can check is a functor very easily. And it is not just a functor, but it is also part of an equivalence of categories, because same thing could be said about G. You can define G op as well. Are you still there, Anita? I'm not sure who I'm talking to.
Again,
Yeah, loudly.
could you please explain the capital F of small f part again? The composition and then the op function of that.
Which one?
The map from f of A to f of B.
This one.
The parallel one.
Huh?
The parallel one.
The parallel one. This one.
To the right.
Okay. So normally what, I mean, do you understand what is the dual category? If there is a map from FB to FA in D, then that is really a map from FA to FB in the opposite category, and we simply write op. Yes, formally reverse the directions.
Okay.
Yeah, there is nothing is changing. You just formally change the domain and codomain of a morphism.
Okay.
Yeah, so now we want to define what happens when capital F op operates on a morphism, but an arbitrary morphism looks like F op. So we define it to be the only choice we have. In category theory, everything is obvious or false. Okay, if you want something to work, then there is a unique choice. So this conclusion that it has to be defined to be FF op, that comes from the fact that F op from A to B in C op is actually this morphism. Associated to that, we have this morphism in category D. And therefore in D op, we have this morphism from FA to FB. So that's the only way you can do it. And therefore, this is the definition of the functor. Once you have that functor, then you can use this definition of a functor to show that it is equivalence of category. It is part of an equivalence of categories. If you still don't get it, then you have to revise your definition of a dual category.
I got it now, sir.
Okay. Anybody else who has any
How
question?
do we show something is not equivalent? Like two categories are not equivalent.
A very good question. I think I will hand over the mic to Deepankar. He has put this question.
Well, I have this mic.
Oh, you have yours.
So, yeah, so in the lecture today, I commented that equivalence of categories show that they transfer almost all properties from one category to another. So in that way, if you can somehow show that an equivalence, if you can somehow show that there are two categories in which one property is there and the similar property is not there in that category, the other category, then you can straight away say that this is not going to be an equivalence. So I guess you were trying to solve that question 8.
Seventh course.
For that,
Eighth
I feel
question.
that you, sorry?
Yeah, 8th question.
Yeah, for that, I'll give you a hint. Solve question 7 first. Did you solve that?
No.
If you have solved that, now revisit your notions and try to convince that every equivalence, this also holds for an equivalence. Every equivalence is an adjunction. So if you have an equivalence of two categories,
then the adjunction also should be there.
Sorry?
Then the adjunction also should occur. Like,
yeah. An equivalence is a particular example of adjunction.
Okay.
Yeah. Devanjan,
Yes.
are you solving any problem right now?
Yes. Currently solving the 8th one. Yes.
8th one. Okay. Did you solve the 7th one?
Yes.
Okay. All right. What about Anand?
I'm looking at the 14th one.
14th one.
The one about abelian groups, like finite abelian groups. So I think my hunch is that if we have a map between two finite abelian groups, so since these are finite abelian groups, they can be written as a direct product of cyclic groups. And my hunch is that if we have a function like a group homomorphism from one abelian group to another finite abelian group, then we can always find another one in the other direction, because like I think it should map one cyclic factor to another cyclic factor, and we can invert along the cyclic factor is what my
So first of
intuition
all,
is.
yeah, okay, I hear that, but to understand this question, first of all, you have to tell me what categories I am concerned about.
What do you mean? Like
So
you mean the category
what
of
was the
abelian group?
problem? 14 was show that the category of finite abelian group is equivalent to its own dual.
Yeah.
So there are two sides.
The two categories
On one
are
side, you have finite abelian group. On the other hand, you have the dual of finite abelian group, the dual category. So to give me, if you want me to give an equivalence, then you should give me a functor from one category to the other, right?
Yes.
Yeah. So which functor do you want to assign here?
So the functor takes objects to themselves, and morphism, like each object is assigned itself. Like on the object is the identity functor, but on the morphism, like I think that, so like I still haven't formulated this fully, but I think that if we have a abelian group homomorphism from one finite abelian group to another, either it's trivial or it maps some cyclic factors to other cyclic factors, and I have a feeling we can construct one in the opposite direction as well. Like I haven't thought this through fully. So yeah, so but my hunch is that you
are
can
not
always
audible.
construct.
Can you speak loudly?
Okay, is it better now?
Yeah, go ahead.
Yeah, so yeah, I actually don't have the full functor in mind, but I know that it must be identity on the objects. Like each object is assigned to itself.
No,
And
I don't feel that you can. Okay, you can try doing that, but here is a hint for you. You look at the lecture. There was one about finite abelian groups, finite vector spaces, finite dimensional vector spaces over reals, and its own dual category. Do you remember that example?
Yeah.
So try mimicking that idea over here. What was a dual to a vector space there? Try mimicking that idea here.
Right.
So
Okay.
it is something called the character of an abelian group.
Okay, right. Okay.
Yeah. So try the character as a functor and then try to solve that. The idea would be exactly similar to what you know about finite dimensional vector spaces.
So characters, from what I recall, are homomorphisms to complex numbers, right?
Okay, you can take complex number, but you can also consider the circle group.
Right.
Yeah. I'm not sure about whether complex should also work as a linear character, but yeah. Try circle, it should work.
All right.
I should have given you this functor, otherwise this sounds so complicated maybe.
Yeah, yeah.
Okay.
Not tutorial. Hello. Can you please pay attention here? I mean, yeah, we can proceed with our tutorial session, but this particular time was designated to discuss student presentations topics. Yeah, so that's why. So is Professor Sujata Ghosh here? Yeah, if she's here, she can.
Yeah.
Yes. Okay, so all the resource persons, yeah, I'm going to stop sharing. All the resource person could be on the stage. Yeah, and we can talk about something for category theory. Okay, so there is an announcement before.
Yeah, so if you have any problem with the given question, then you can email us maybe at the ISLA ID.
Yeah. So, yeah, let us start with this. So the idea, so in the last installment of ISLA, which was organized by Sir Bhopal and which was also online, we started with this, that on the second day of a 6-day school, we assign some topics to groups of people. The students have to work in small groups, read about something extra, because whatever topics are covered in the class, yeah, they are in a compact form. And you might, if you are interested in a particular topic, you might want to explore it a little bit further. And not just that, but also show it off. Yeah, in some sense, you can show it in front of the people who have taught you. So, in order to give you an opportunity, the last day of this school will have only one lecture, and after that, we just have a student presentation session. So you can, if you are shy, then maybe you want to try it for the first time, and the audience will be very small. Audience sizes, yeah, I mean, currently we just have 19 people, so don't feel bad. Most people don't even show their faces, so not many people are looking at you. So I just want to encourage you to participate in this. We'll write down a list of topics, we'll suggest a list of topics, and if you need help from us in order to find the literature, that also we are willing to do. And it's better if you work in groups, so that maybe one person might not understand one concept, but the second person understands it well. So working in groups is always helpful. So that way you still have 3 days to prepare for a presentation. You can either do it on board if you are sitting in this classroom, or you can prepare a short slides presentation and present it online. So in any sense, we want to encourage you to learn something extra apart from what is being done. And as a bonus, your talk will also get recorded on YouTube. Yeah. So that's the idea. Sujata, do you want to add anything?
No. Fine. That's the plan we
Okay.
have. So please go on.
Okay. So we have prepared a small list of topics. So maybe we'll start with the first instructor herself. Sujata, do you want to explain in 1 or 2 lines each topic? We can write them down on, yes,
Yeah,
write it on this, but she can explain a bit.
So I'm not sure about the third topic. I was planning to present it, but then I decided not to. So has that been presented? Has that been presented? I don't know. So has Zonslema been presented? So otherwise,
No,
doesn't make
I don't
sense.
think anybody will do that.
Okay, so then let's leave it. So the other 2 topics. So what I had was complete lattices and fixed point theorem.
Yeah, complete lattices and fixed point theorems.
So I have just covered some things on complete lattices. So there is a very nice fixed point theorem, which is termed as the Naster-Tusky fixed point theorem.
Yeah.
Monotone maps. So maybe one or some of you can study that and present it, and maybe say more about complete lattices and related issues. So that's one idea that I had. If you would like to, if anybody likes to talk on this topic, you are very welcome to just send me a mail, drop me a mail, and I would be happy to suggest references and things like that. The other thing I suggested is chains and anti-chains. So there was an exercise in class, like I have given you yesterday, which kind of which had some connection between chains and anti-chains, and there was a question like whether it's a tight bound or not, and I was talking about like it's given by Dilbert's theorem. So that is another thing that you can kind of study on your own on present, or whatever things that you may come up with regarding. There are lots of interesting stuff that is happening. You can dig it up on the net, you can find loads of stuff, and if you are interested, you can present that, like something related to chains and anti-chains as well, such as ascending chain condition, descending chain condition. There are lots of other things as well. And then there are related stuffs which is not even there, like well-ordered sets, well-found, like we have talked about partial ordered sets. What about well-ordered sets? That's also kind of there, which you can think about. But one thing what I would like to reiterate, that please, like, you are not, like, these are just suggestions. If you want to do something else, you are very welcome to do that as well. Yeah, over to you, Amit.
Okay, I mean, I don't see any problem with Zon's lemma and applications. That could also be one of the topics if they haven't seen. And
yeah,
yeah, Zon's lemma and applications.
So let me. So was there anything discussed on ultra filters today? After
not yet. Not yet. No.
Okay. So let me give you why I thought of this topic. Was that, like, when I mentioned that filters, I defined filters today, and I said that maximal filters, another name for maximal filters is ultra filter. And so, and I also mentioned that any filter can be extended to an ultra filter. So some such result to prove such results, you actually need axiom of choice or another version of axiom of choice, an equivalent version of axiom of choice, which is basically Zorn's lemma. I'm just giving you jargons now, you can look it up. There are loads of references everywhere. So you can actually go into that result, see the application of Zorn's lemma, see kind of other applications of Zorn's lemma as well. And I can very well vouch for it that it is really captivating if you once get into this. So I can definitely vouch for that. Anyway, yeah, now over to
Okay,
you.
okay, thanks. The theory instructors together. What is the first one?
Well, adjoint functor theorem.
Adjoint functor theorem is one. We have just started. Yeah, you can write it down. So yeah, you can, yeah. So Freud's adjoint functor theorem is something that is one of the most important results in basic category theory, and we will look at the converse of it tomorrow. So this is one important thing. Then another one was functor categories and Yoneda lemma.
So this is also in the tutorial. This is also in the tutorial, but you can use this for presentation, I guess.
There is so much that can be done about Yoneda lemma. Anay? Yeah. And Nick has also sent us some topics. Anay, can you read that?
We are going to assign students now?
No, let them decide.
Then when they will come up with the idea, like which group is working on that?
Well, if somebody wants to choose it right away, we are happy to let them.
Let us finish the
Yeah.
topic first.
Here are some topics by Nick. So first one is bitopological characterization of Priestley and Essakya dualities.
This is an advanced topic. You haven't yet seen, most of you haven't seen anything about it yet.
Priestley and Essakya dualities. Essakya.
But those who already know something about it can think about this. Yeah.
The next topic is.
Yeah, next topic is what?
Duality for modal algebras.
Okay, duality for modal. Yes, Anand, you can talk.
No, sorry, that was my mistake.
Okay.
Excuse me.
Yes.
Can we choose some topic that is related to the category theory and the function space?
Yeah, sure.
That how the category theory is influenced to the topological function space. Because actually my students is also participating in this workshop, so they are working on the topological function space. So
right,
is it possible when you can also give this such topic? Simple category theory, how the category theory influence the topological function space. They can.
I mean, I don't think any of us have any expertise in topological function spaces, but in general, function spaces are like representable functors.
Yeah. It is not much more expertise are required because Because the category theory is very well known. The application in the topological function space is very advanced topic. So if possible, you can.
If you have any particular thing in mind, then maybe you can ask your student to do that.
Yeah, definitely.
Any other topics?
There are two more topics.
Yeah.
Algebraic and dual characterization of subdirectly irreducible lighting algebras. Algebraic and dual characterization of subdirectly irreducible lighting algebras.
Well, yeah, before we go further, I would like to add one, like quantifiers as adjoints.
One question was there for Boolean algebras.
As adjoints. So this is very much categorical logic. I will certainly talk about it, but I won't cover it in detail. So there are things to be done. And 10th one.
Yeah, there is one more by Nick. I
Okay.
think it will be better if you write in this.
Okay.
It will
At the bottom. No, that's the last one.
Yeah, I will have some.
Okay,
Oh,
then-
yeah, sure.
then
So
write.
start writing here.
So you want to show the whole board?
Yeah, it will be
Yeah,
better
that's
for them
why
to
perhaps we are trying. Yeah. Okay. You can change the camera.
I was thinking that I should include the students there, so that's why I put that.
Right.
Yeah.
Yeah, so the last one, he has mentioned it to be more advanced. So this is amalgamation in varieties of fighting algebras via duality. In varieties of fighting algebras.
Fighting algebras. In varieties of fighting algebras.
Via duality. Via duality.
Any more?
No, that's all.
You want to talk?
Yeah, I just wanted to add something.
Yeah, okay.
Yeah, please finish it, then I will suggest something.
Do I need it? So one of the topic could be cylindric algebra. Because I'm going to cover the first order logic, and we already saw that Lindenbaum-Tarski type of algebra for propositional logic was Boolean algebra. So there exists some idea about the algebra corresponding to first order logic, and that is known as cylindric algebra. So you can have a look at it, like what kind of algebra it is and how they can relate it with the idea of first order logic. Yeah, Sujata Di, please.
Yeah, I was just wondering that there are some computer science students here.
Yeah.
So for them, I would suggest, if you are in, of course, you can do all these mathematical topics, but if you are also interested into studying some computational aspects, like you can very well go into computational aspects of these kind of algebraic structures. So you can think of
computation.
That is, yeah, computational aspects.
Of?
Once, I'm just putting it general, all these the different algebraic structures.
Something, whatever is.
Yeah.
Plot.
So
Okay.
because there are various studies.
Okay.
on
So,
that.
okay, any more? We have lots of, we don't have that many students, I guess.
We'll send an email out to
Yeah.
everybody. Yeah.
So I can add one more, like you can it is just a general idea, like you can think about the homotopy because it is very much hot topic to work on together with logic, I mean type theory as well. And I already gave a hint during my topology course. At the end, I talked about some kind of topology defined on the continuous, collection of all continuous functions between two spaces, and that will lead to the idea of the homotopy in some senses. So that's why you can think about like as a topic. It's a very broader thing, but you can choose as whatever you can. Okay, so any other thing?
We can add completeness theorem for propositional logic if they are looking at it for the first time itself.
Yeah, that I'll, yeah, okay. Completeness, right?
Completeness for PL.
Completeness for propositional logic. And last one, maybe it is very some kind of easy stuff, is like survey of topology. So that means like whatever, like you will go through some of the dualities, like already you heard of one about the stone duality. We are going to know about the Priestley duality and Esakia duality throughout our lectures. So that project is about like whatever dualities already worked on about the algebra and topology, like how many of them you can find, not only find, but try to understand what structures they are. I mean what algebra and what topology and what are the functors roughly. Then only just try to, think about it and write down in your own language that what algebra and what topology are related and what are the functors between them, more or less. So that is the idea of that 15th one. Anything else? So that's it, I guess.
If there are people who want to choose one topic right now, please let us know. Yes, Nitish. Duality for modal logic. Nitish is choosing that. Okay.
Yeah.
Okay. Anybody else from online? Yeah.
I am interested to do the first topic, complete lattices and fixed point theorem.
Debanjan, yeah.
Yeah.
Which topic? Loudly.
Complete lattices and fixed point theorem.
Complete lattices and fixed point theorem. Okay. Jaskirat?
I wanted to ask that dualities for model logic will be like something different from model logic, dual nature of model logic, or is it model logic itself?
You can contact that person. We can provide you the email, and I think he has also provided some material to read.
Like I can go for model logic, temporal logic, arrow logic.
So if you want, then you can work with Nitish and.
Sure, we can.
Yeah.
Jaskirat. JSKIR8. Yes.
Yes.
Thank you.
Okay. Anybody else? Yes, online participants, do you have any preferences? You might form your groups right away and work together.
So, well, I'm not sure yet. Like I still have to go through the list of topics, but I have one in like probably something related to like the Unit lemma and like a computer generated proof of it.
Okay, fine. Anand, fifth one. Yeah, you can choose what you want to do there. Yes.
Yeah, I haven't made up my mind about the topic, but maybe something along these lines.
Yeah, sure. I mean, preferably by tomorrow, if you give your preferences, then you can form a team and start working. Yeah, you don't have many days. Yeah.
Okay.
Yeah. Anybody else from online or offline?
How are we supposed to like give our preferences? I mean, through email or?
Yeah, I mean, we'll circulate a Google form
Oh,
if that's what you want,
okay,
or
so
you can
I-
email us. That's also fine.
So
Yeah,
actually,
better
I
you
had
send the email.
okay. So actually, I had a query. So I mean, the contact details of our group members. How are we going to acquire that?
And that we will facilitate. You just
Right,
let us know
right,
what
right.
topic you are
Understood.
interested in.
Understood, sir.
Okay. Anybody else?
Sir, I'm interested in the complete lateral lattices and fixed point theorem.
Okay.
Suyash.
Suyash Pathak. Anybody else?
Yeah, hello.
Yes.
We're interested in doing a presentation regarding representation between game algebra and game board algebra. But we're still not sure. But we'll send you and also the thing is it doesn't belong to any of these topics. I mean it is algebraical in some way. But yeah. So
Yeah, you can do it. Yeah.
Yeah.
I hope there is some logic and some algebra involved in that.
Yeah.
Yeah.
Okay.
So that's okay.
Yeah.
Don't make it a research level presentation, Avijit. Yeah.
Yeah.
That's all.
Okay. Okay.
Yeah.
Yeah. So how much time are we getting? Any idea? Like 12?
I mean, usually 15 to 20 minutes, you won't have enough time to prepare for more. Unless you have already done that before the beginning of the school, which is not really fair.
Okay. Yeah. Yeah, thanks.
Okay. Yes, anybody else? Yes, Manan? Huh? Okay, completeness theorem for propositional. He does.
Maybe you know it.
That's okay.
Okay. Why are you trying to do that? Your name is?
Manan. Okay. If anybody else wants to choose something, please let us know. Neha, you have unmuted yourself. Please tell me.
Sir, I want to go for the seventh one, development of model logic.
Dualities for modal logic. Okay. Neha Gaur. Yeah, so that's a nice group. We have finished that topic. You can choose to give either one or two presentations. Yeah, that's up to you. Or all three can present individually. That's also okay. Yes, anything else? Okay. In that case, we'll declare that this meeting is over. And by tomorrow evening, we will definitely let you know who other people are. We'll send out an email to all the participants who are absent today. They will know that these are the topics. Huh? Yeah, okay. We'll send out a Google form and then you have to submit your preferences. Even if you have said so already, yeah, that organizers will find helpful to manage. Okay. Thanks a lot. So hope to see you tomorrow at 9:50 again.
Thank you.
Thank you. Take a picture, Anna. Bhargav, you haven't chosen anything.